Okay, and let's have a quick look or quick review of what we have done on last Thursday. So we have in the for equilibrium of rigid bodies, we have summation f equals to 0, and because we have and for most rigid bodies we have supports, and we have supports. We have supports on the ground or with other rigid bodies. So we need to know what to write or what to draw as supports. For example, that we to determine what to write in or what to draw in rigid bodies, in frequent diagrams, we first look at whether it can move in a particular direction. For example, if the rigid body can move in this direction, that means we don't have force in this direction. But because in this cable we cannot move in this direction, so we have a force in this direction. Okay, and for the most important ones are numbers 1, 3, 8, and 10. Numbers 1, 3, 8, and 10. And number 3 is we call a roller support. A roller support. And number 8 is a hinge support. And for example, for number 8, and this bar can rotate, but it cannot move horizontally, or it cannot move horizontally, or it cannot move vertically either. So we have forces in both horizontal direction and vertical directions. So we need to draw two forces, or sometimes the force is acting in a particular direction, and you can simply draw a single force with an angle here. Sometimes you can sometimes we do this, and sometimes we do this. In this case, we need to know the angle phi is known. Sometimes. I will talk about this later today. And for number 10 is we call a fixed support. For a fixed support that like poles on the for the power supply, it means we cannot move in the vertical direction, we cannot move in horizontal direction, and we cannot rotate. Right? So we have both forces in horizontal direction, vertical direction, and a moment here. So let's we talk for a whole week on these things, and let's talk about let's work on an example. Page 40. So, and in this case, we have a frame. We have a frame. And supports part of the roof and a small building. Knowing that the tension of the cable is 150 kilonewton, determine the reaction at the fixed end E. So, and the roof is this one. And so we need to what do we know? We know the tension here is 150 kilonewton. And what do we want to determine? We want to determine the reaction at the fixed end E here. So it is a fixed end, and so and is there any words that we don't know? It seems I think we know the other words. Now, because this is in this problem, we will we will use this, right? Summation f equal to 0, right? Because it is in equilibrium. So we need to draw the free body diagram. So first of all, we work on the free body diagram. What are the key points in the free body diagram? And let me take a quick look. And it is on page 36. So we have in the free body diagram we have three things. Contour, external forces, and dimensions. Okay, these three things. Contour, external forces, and dimensions. Now, and for the next let's go back to our problem. And so we need to have this one. You don't need to write this, and this for me you don't need to write this. Okay, so we need to have the contour. We need to have external forces. Sorry, external forces only. We don't need internal forces. And we need dimensions, right? And now, and there is one thing, and we put so what is our for the free body diagram? For the free body diagram, where is our free body? Where is our free body? I give you a tip. I give you a hint. Now, everything we want to determine is here, right? At point E, and the tension is the cable is known. So for these quantities that we need to determine, I'll write it down later. For these quantities we need to determine, all of them are at the boundary of the free body. Okay. Okay, so in here for the forces to be determined, because we need to determine these forces at E, so it needs to be at boundary of the free body. And because this 150 kilonewton is also, it needs to be an external force. So it is also at the boundary of the free body. So we first need to determine what is the free body in our free body diagram. For example, in this case, we have we need to determine these forces, and so it needs to be on the boundary of boundary. On the boundary of free body. Okay. Now you may now let's draw the contour of the free body, and let's draw it. And this so we need the contour. So we need the shape, the rough shape of the free body. Okay, like this. please go with me because I will do it step by step. Okay. I'll do step by step. And for the contour, we also mark the points on the points on the diagram as well. Sorry, please. Like this. So we have 6 points in the figure. So we mark all these 6 points. So we draw the shape of the free body. Of course, we don't need to draw this, and we don't need to draw this either. These are two details that we don't see this. Now the next point is so we have now drawn the contour, and what do we draw next? The external forces. Okay. Now when we draw the external forces, how many external forces do we have? And firstly, we have those 4 forces, those 4 20 kN forces. These should be drawn here. And we need to write down the magnitude. So we have these 4 forces, and what else do we need? Now, because if we only have these 4 forces, we do not have equilibrium, right? We do not have equilibrium because summation F does not equal to 0, right? So we have other forces. We have tension. Okay, very good. So we have because the boundary of the free body is here. It is here. So the tension of the table is here, and this is tension T here. We don't know. Do we know the metal? Yes, and the metal is 150 kN. So it's here. Do we have equilibrium now? Or can we have equilibrium now? The answer is no, because all forces are going down. All forces are going down. We don't have forces going up, right? So where do we have forces going up? At point E, because this is the support, right? This is the support. So this is a fixed support. So this is a fixed support. And for this fixed support, can it move to the left and to the right? Can it move to the left or to the right? No. Okay. So we have a force Ex here. So it has a force in the horizontal direction. Next, can point E move up and down? No. So we have a force in the direction of in the vertical direction E y. And the first thing, can it rotate? Can point E rotate? No. So we have We have M, E here. It's okay. Because point E cannot move horizontally, it cannot move left and right. So we have a force. You can draw it on to the left or to the right, it's up to you. And of course you can draw it like this, and it's okay. But I want to do it this way. And now because it cannot move up and down, so we have a force in the y direction. The last thing is, can this rotate? Can it rotate like this? No. So we have a moment here, ME here. It's okay. So the biggest problem for your seniors in working out on free-body diagrams is that they always miss one or two forces, and if you miss forces in this step, then there's no hope you can do the rest of calculations correctly. Okay. So if you have problems in this at this step, then you will definitely have problems in the next steps. So please take some time in drawing free-body diagrams and in the homework. Now we have next, and so we have all the external forces. And the last thing is that we need to write some key dimensions. So for key dimensions, and so we have for example, we need to we have these distances, these dimensions, and this one is 1.8 meter each. And what else? We have this theta. This force has the angle of this force is known, and theta is equal to how much? Theta is equal to tangent arctangent of how much? 4.5 divided by 6. Take a look of the diagram. Because this one is 6 meters, and so and this is our free-body diagram. Three elements. The first one is contour. The first one is contour. The second one is external forces. And the third one is dimensions. Okay. So from this is our free-body diagram, and from now on, and please take some time to make a drawing. Now for is that okay? Any problem with the free-body diagram? Remember chapter 4 and chapter 6, and coming on will make at least 1/3 to 1/2. I mean 33 to 50% of the whole subject mark. So take some time in working that out. I will give homework, and TA will show you examples at TA class. But if you think you are not good enough, you can work on more homework. Now we come to after we draw the three-body diagram, we come to equilibrium equations. Now we have as I mentioned in chapter 2, if you are not confident enough to do the mathematics, you first write these two. So equilibrium equations actually means these two sets of equations, right? Summation f equal to 0, summation f equal to 0. Now we have in 2D problems, we actually means these three things. The first thing is summation f(x) equal to 0 and summation f(y) equal to 0 and summation m equal to 0, right? To help yourself and at this step, the only problem that your seniors have is to make the positive and negative signs correct. Okay. To make the positive or negative sign correct. And remember that, at this step, that the only problem is whether you make the positive and negative signs correct. And I think you can handle this. Now, to make sure you have the signs correct, we usually do this. We have, for example, for summation f(x) equal to 0. For summation f(x) equal to 0, we will write like this, and we define the positive direction. For example, if we think towards the right is positive and towards the left is negative, we will write like this. This is also the method used in the book. Okay, so we write the right arrow and then we write the plus sign. We write the positive sign. It means that this is the positive direction and this is the negative direction. It's okay. Now for example, if we have a summation f(x) equal to 0, so what are the forces in the which forces have x components in this problem? We have first of all we have Ex. This is in the x direction, and this force 150 kilonewton has an x component here, right? We have x and we have y components here. So it means are there any other forces that has x components? It seems not. So we have it means we can write it. Oh, sorry. We can write Ex plus 150 kilonewton sine theta equal to 0. Okay, Fx equal to 0, it means we have Ex plus 150 kilonewton sine theta equal to 0. So the next thing is summation Fy to 0. For example, we can say we have positive is going upwards and negative is going downwards. But If you think I'm writing too quickly, then raise your hand and I will stop, okay? Now, and for summation Fy equal to 0, we have many, so we count how many forces, we have Y components. We have these 1, 2, 3, 4, 5, and 6. We have 6 forces having Y components. So, and we first write EY. EY is going up, so it is positive or negative. So is it positive or negative? Positive, okay. EY. And then for the 150 kilonewton, is this positive or negative? Negative going down because it's going down. So it's 150 kilonewton cosine theta. And for these 4 forces, they are going downwards, so they are negative. So we have 4 times 20 kilonewton equal to 0. For the last point, and summation m equal to 0. And for 2D problems, and we do 2 things. First of all, we define the positive direction. Usually because we have x and we have y, so the z direction is going out. So usually we have this one is positive. This one is down because it helps you getting the correct results. Now this is the first thing, and you mark the direction of positive moments. And the second thing, please do another thing as well. And of course, we know that the summation m equal to 0. So you can take any point and you will have summation m equal to 0. But because we are writing down the moments out, so please write down your reference points. For example, in this problem, for example, we want to use point E as the reference point. So we write down E here. Therefore, we have so we now come to counting the forces. Because EX and EY, these 2 forces go through point E, so the moments are equal to 0. So these two will not have moments. And so we need to count the rest. And for ME, it is going anti-clockwise. Anti-clockwise, we say anti-clockwise is positive. So this one is also positive, okay? So this one is ME. This one ME is positive. And what else? We have these 4 forces, and all of them leading to moments. So are these positive or negative? Positive, okay? Very good. And so we work on, I write it in this way: 1.8 plus 3.6 plus 5.4 almost 7.2. And do we have other forces to that have moments? We have done this and we have done this for what else? Okay, this tension, yeah. So for this tension, and this is going in the clockwise direction, so it is negative. So we have 6 times 150 kilonewton times sine theta equal to 0. And I think you can work on the numbers and get these 3 right. Okay. And for your results, you can in my examination you can do this. But if you go to examination outside to other universities, you may write in this way. Okay. So because this is minus negative 90 kilonewton, so it is because we have positive is to the right, so this force is going to the left. And so on. And because this one is plus 20 kilonewton, so because plus is going upwards, so EY is 200 kilonewton going up. Okay, and for ME equal to 0, and this one ME is plus 180 kilonewton meter, and this anti-clockwise is positive, so ME is 180 kilonewton meter anti-clockwise. So, but if in my examination, you can write this. Okay. Take your time in writing all the results. And last but not least, I want to mention one thing. In the problem, I'll come back to here. But in the problem, we have the free body. We have the free body defined like this, right? But you may say, oh, we have tension. Tension of the cable is 150 kilonewton, and of course, the tension here is also 100 kilonewton, for example. Now, can we define the free body like this? Can we do this? The answer is yes. Okay. The answer is yes, and we come to here. Now, for example, if we have the free body defined like this, if we have the free body defined like this, and we also have all these forces and forces going here, right? And because we have the free body, the boundary of free body is here. So this part of the cable will pull the structure in this direction. We have TBD here, right? And this part of the cable will also have a force acting on point B, and the TBD is here. And because if we consider this part of the cable, of course, these two forces are the same, right? These two forces are the same. So by action and reaction, so we have forces like here. Is that correct? And by you can work it out from physics or mathematics that if we do it from physics and do it from statics, this force, because this is a rigid body, this force can be moved along the line of action to here to cancel out this force. Okay, that's the first way of explaining this. But if you don't find this, and let's erase it. Let's do it from this way. So if we have these two forces, right? We have these two forces. And if you put these forces into these three equations, you can see these two forces will cancel off each other, and you can get the same results. Okay, you can get the same results if you put the free body like this one. You can try it at home. Before I take a break, let's have a quick review of the